So let's start looking at what these deformed rectangles look like I was stretching out the trash bag in the previous video. So if you want to switch from, we're in 2 dimensions now, from coordinates x and y to u and v, then we have these little rectangles du by dv in the uv plane, and over in the xy plane it's going to be some deformed looking rectangle. And we want to estimate the area of this rectangle. And in order to estimate that, we're going to look at these vectors. So here's the vector A, and here's the vector B, and these are basically the vectors pointing out of one corner of the rectangle. And if this initial rectangle is small enough, this deformed rectangle is also going to be really small. So we can actually approximate it if we make these the correct length. Sorry, I shouldn't be doing that in highlighter. Let's do this in black. If we make these the right length, we can approximate this by the area of an appropriate parallelogram. Okay, and then you maybe remember from Math 126 that the area of a parallelogram is just the absolute value of the cross product. So if we can figure out what these vectors are, then we can figure out what the area of this parallelogram is and the approximate area in the xy plane of this nice rectangle over here in the uv plane. So let's think about what these vectors are. Well, the A vector is related to du, except we're over here in x and y. So if x and y can be written as functions, like x can be some function of u and v, and y is also written as some function, call it y of u and v. Then the A vector, the x component, is going to be based on how much the x changes in the u direction. And then the y component is going to be based on how much the y changes in the u direction. And then same thing with B. We'll have now changing in the v direction, because now we're taking dv and converting it into a vector in the xy plane. So x and y changing in the v direction. And then their magnitude is going to be related to how big du and dv were originally. So we need that as scalars at the end. And then we're about to do a cross product, so we actually need to promote these vectors to 3 dimensions. So that's easy. Every vector in 2 dimensions exists in 3 dimensions. We just keep them in the xy plane, put a 0 coordinate there. So the area of our stretched out rectangle in the xy plane is approximately the absolute value of A cross B, which is the absolute value of xu, yu, 0, these are partial derivatives, cross xv, yv, 0, and there's a du and a dv at the end. Okay, so now we can write this cross product as a determinant. Hopefully you remember this at least vaguely from 126. We write just always vectors I, j, and k at the top. There's other ways to calculate this too, but this is my favorite one. Write your first vector, your second vector. When it's absolute value, order doesn't even matter, so that's great. And then there's a du, dv as scalars out here. And then let's recall how to calculate cross product. We can expand along the top row. We can actually expand along any row and column for determinant, and I'll talk about this a little bit more later when we do this for when we do the conversion for spherical coordinates. But for now, let's expand along the top row. So we have I, and then we cross out that row and column, and we need to take the determinant of this 2 by 2 matrix, which is 0 minus 0. So that's I times 0. Next we go to j, cross that out, take the determinant of the remaining 2 by 2 matrix, that's also 0 minus 0, so plus j times 0. And then finally, going to k. My dog is sneezing in the background, apologize for the noise. Cross out that row and column and take the determinant of that 2 by 2 matrix. So the cross product is going to be 0, comma 0, comma, xu yv minus xv yu du dv. And now this is just a vector pointing in the z direction. So the absolute value is just going to be the absolute value of that z coordinate. So xu yv minus xv yu du dv. Okay, and this isn't very interesting as a formula. Really, the interesting thing is, well, a couple things to note. There's always going to be zeros there, because we're always going to be working in 2 dimensions and promoting to 3 dimensions. So that means those first 2 determinants will always be 0. And so the only thing that's important is when you expand along that k, unit k vector, cross out that row and column, and then you'll get that determinant there. So we call that the Jacobian. That's a matrix. And then basically the factor, when you have a double integral of some function dx dy, we want to switch to double integral of some factor du dv, and we've got to multiply by a thing. For example, in polar coordinates, it was r dr d theta. So like we got to calculate what that r is, or whatever it is in the coordinates we're going to. That thing is going to be the determinant of the Jacobian. And in 2 dimensions, the Jacobian is this 2 by 2 matrix. Let's say determinant is the 2 by 2 matrix, and then we're going to have xu, yu, xv, yv. And where it comes from is the absolute value of that cross product to get the area of the parallelogram. So we did all that to show you, but the only thing you need to know, really, is this for calculating what that factor we multiply by in the integral is. So let's do an example for polar coordinates. So instead of u and v, we're going to have r and theta. R theta instead of u and v. And so remember, we wanted to write x and y as functions of the new variables, right? So let's do that here. We're going to write x and y as functions of r and theta. Well, we already know how to do that. X equals, let me do this in black. X equals r cosine theta, and y equals r sine theta. And then I just need to calculate this Jacobian. So I need to calculate xr, yr, x theta, and y theta. So those are partial derivatives. Partial derivative of x with respect to r. Cosine theta is a constant, so there's that. Partial derivative of x with respect to theta, we get negative sine theta, right? And r is a constant. Partial derivative of y with respect to r, we get sine theta. And partial derivative of y with respect to theta, we get r cosine theta. There's the Jacobian. We need the determinant of the Jacobian. You might not need to do all this writing, but so we'll use a vertical line, which is sometimes the notation that books use for determinant. So you're certainly welcome to do that. And really, we need the absolute value of this determinant. So just note that if it's negative at the end, we'll multiply by -1. Okay, so we take r cosine squared theta minus negative, there's a negative there, so really it'll be plus r sine squared theta. And then we can factor out an r, and we get a cosine squared theta plus sine squared theta is 1. So the determinant of the Jacobian there is r, or maybe absolute value of r. But if you think of polar coordinates a certain way, you can keep r positive. Anyways, that's exactly what we wanted, right? The determinant of the Jacobian was going to be the thing that went there. And remember, in polar coordinates, we're always integrating a thing, and we have an r dr d theta. So all that work was to get that r. And we've looked at the reason why that r is there geometrically as well, but now we can do it algebraically.